I think it's time.
Okay.
So, Pasha, should we wait more? Okay. We're very pleased. Welcome everyone to UCLA Combinatorics seminar. We're very pleased to have Nicolle Gonzalez from UCLA, who will tell us something in a small font from symmetric functions to everything else. Welcome, Nicolle.
Hi, everyone. Thank you so much for the invitation. I apologize for the small font. Clearly, I forgot how to give talks in person, and I'm used to Zooming. So if you can't read anything, just let me know, or if anything's not clear because of the projection, obviously.
Those who are on Zoom actually can make it bigger.
Yeah. I'm talking to you guys, actually, here in the audience. So the title is just From Symmetric Functions to Knots and Back Again. So what I'm going to tell you about is work in progress, or joint work with Matt Hogenkamp. So let me give you essentially a bit of a rundown of what the talk is going to entail, at least the motivation initially. So our main player is going to be an algebra known as AQT. And the original place where this algebra came into play stems from a well-known combinatorics conjecture known as the shuffle conjecture. And fundamentally, what this conjecture told us is it gave a combinatorial formula for the Frobenius character of the space of diagonal harmonics. Now, I apologize because I realize that this is a little bit hard to see here in the audience and live, but this is basically the space of diagonal harmonics is nothing more than you take polynomials in two n variables, so n variables in x and y variables, and you take them subject to the condition that the sum of all possible partial derivatives is 0. So that's the space of diagonal harmonics. And the conjecture basically said that we can compute its Frobenius character through some combinatorial formula. In particular, the specific conjecture told us that this space of diagonal harmonics, which was already known through work of Haiman, or its character was already known through work of Haiman to equal the action of the nabla operator on the nth elementary symmetric function. The conjecture stated that this was equal to this big sum, right? So this is a sum over dict paths and word parking functions, where you have t to some statistic known as area, q to the din, again, another statistic on word parking functions, and some monomials. So this was this big combinatorial conjecture. And for context, if you're not familiar with the nabla operator, it shows up a lot in the theory of Macdonald polynomials. It has eigenfunctions, Macdonald polynomials, and it plays a big role. So this was, very meaningful that you could find an explicit combinatorial expression for its action on En. Generally, its action on things is not well understood. So this was open for 14 years. And finally, it was proven. It says theorem here in very light, almost vanishing green. This was proven after 14 years by Carlsson and Mellit. And the way they did it, and the reason that this, in some sense is such an interesting proof, is that they didn't do it through traditional combinatorial methods, which is what a lot of people had spent time doing, but instead they introduced a new algebra known as AQT, and they defined a representation of that algebra over a family of vector spaces, which you probably can't see because this is microscopic, but this is, so we're going to call them Vn, this family of vector spaces, and we're really just going to think about this as symmetric functions in variables x over the ring of QQT, so coefficients in QQT, with coefficients y1 through yn, so tensored with polynomials in y1 through yn. Right, so here's Vn. So for example, V0 in this context is just the ring of symmetric functions because you don't have y's. V1 is going to be the ring of symmetric functions where the coefficients are allowed to carry a polynomial y1. V2 carries y1 and y2, and so on. So what I'm going to tell you about is essentially this whole construction, and then I'll tell you how to construct a skein theoretic, which is to say a diagrammatic or topological version of this algebra. So a little bit of context, and this is mostly just for kind of a big picture if you want to know how this algebra fits outside of combinatorics and why anyone, or at least I, would care about it. So there's a big series of conjectures currently that relate basically all the areas that you see here, right? So we have Dachau or Cherednik algebras on one side, which are connected to elliptic Hall algebras. We have in algebraic geometry the land of Hilbert schemes. We have in categorification or Hecke algebras the land of Zirkel bimodules. And then, of course, algebraic combinatorics. And all of these different fields are known through work of famous people like Haiman, or through work of Gorsky and Vazirani, that are related through QT Catalan combinatorics. Or more recently, they're conjectured to be related through these big conjectures known as the GNR, or Gorsky and Rasmussen conjectures, that tell us things about the homology of torus knots. So these are very, very deep and difficult conjectures that essentially relate things in algebraic geometry to things in algebraic combinatorics and things in low-dimensional topology. And it turns out, and I'm happy to discuss this after the talk if anybody's interested in some of the specific connections. Turns out that AQT is somehow nicely sitting in between all of these different fields, right? A lot of the arrows that I drew underneath it in red are conjectural. They're not known, but there's a lot of proof to motivate that they might be true. Turns out that AQT, this algebra, wasn't just invented in a vacuum. It has very specific connections to all these other fields, right? The blue column is things that are already proved in this diagram, yeah. Right? And essentially, so this algebra AQT, which I will tell you what it is known to have a geometric realization in the land of parabolic Hilbert schemes. Obviously, it's related to the land of algebraic combinatorics. That's how it was created. It's known to contain the elliptic Hall algebra. It's related to Dahas, and we'll see a little bit more in a second, roughly how they're related. And then our contribution, Hogenkamp and mine, is precisely to relate AQT in some sense to the category of circle bimodules. I will not tell you about this story today, because that entails categorification, but I will tell you the groundwork for that setup. And again, happy to discuss this later. But what I will tell you about is how to relate this to skein theory. Okay, so that's kind of the roadmap, the global worldview of where this algebra fits and why, if you're interested in any of these areas, you might be interested in this algebra. So what is it? Of course, if you have any questions, stop me at any moment. Okay, so what is the AQT algebra? Sometimes, or at least we've been calling it the Carlsson and Mellit algebra since they're the ones that invented it. And what it is it's an algebra over QQT. We're going to think about this as an algebra with idempotence that is generated by Ti and Ti inverse. We're going to think of Ti and Ti inverse as generators that go from the idempotent 1n to 1n. We have d plus star and d plus that go from n to n plus 1. These are kind of raising operators. We have d minus that lower, so they go from n to n minus 1. And we have these operators phi and phi star that are really just commutators of the d pluses and the d minuses. I'll say a little bit more about why we have these generators in a second and a nice way of thinking about them. But alternatively, if you like quivers, you can think about QQT as a quiver algebra, where you have essentially little nodes, right, labeled by integers. And you want to think about the TIs as being an arrow that stays in each node, right? They go from 1 to 1 or from 2 to 2. And you want to think about your D pluses, both starred and unstarred, as moving you up the nodes, and the D minuses is moving you down, right? So kind of this very vanishing picture here in blue. Okay, now this AQT algebra has a slew of relations. I'm not going to spend any time telling you what the relations are. If you just look at them, they're really not particularly helpful. The key point here, though, is that the AQT algebra is essentially two copies of an affine Hecke algebra, right? And the point is that you take these two copies of an affine Hecke algebra and you glue them together. You add some extra relations that tells you, okay, I have these generators of the affine Hecke algebra, I have these other generators of the affine Hecke algebra, and I add some relations to make them interact in some very specific way. Exactly. So the TIs are the generators of a finite Hecke algebra. That's what these are. The Hecke algebra relations are exactly these relations right here. Now, it's not explicit in this particular presentation, but, and it will be in the next slide, but you have extra generators, we're going to call them YI, which are essentially polynomial algebra generators, that you can construct from these phis that give you the affine Hecke algebra copies that are living inside there. So you have a Y and you have a Y star, you have a TI and a TI inverse, and this is giving you the two copies of this affine Hecke algebra. And these relations here are essentially telling you how to glue the starred operators and the unstarred operators. And you want to think about the starred and the unstarred operators as being these two copies of the same algebra. Because they satisfy exactly the same relations once you go from starred to unstarred. Now, why is this interesting? Because if you're familiar, yes? Yeah, so they're in this page that I was going to get to afterwards. Yeah, so let me just skip ahead and we'll go back to the other one. You can define these operators yi as, phi composed with a bunch of t's, where phi is this commutator, and then you can reduce the previous presentation. Instead of having a phi, you have a y. So it's just an alternate presentation of the same algebra. And then here you have these are the affine Hecke algebra relations. So what I was saying was, the reason that this is interesting, at least if you work in the world of Dahas, is that the double affine Hecke algebra is analogous. It's you take two copies of an affine Hecke algebra and you glue them together, right? And you do the same trick where you add some, in particular, 3 relations that tell you how these two copies interact. This is, in essence, an analogous construction, except these 3 relations are honestly different, right? So the Daha and the AQT are not the same. One is not contained inside the other. And in some sense, it's a question to understand how these two algebras are precisely related. There is a precise statement about, we're going to see a representation of this AQT algebra. There's a very precise statement about what happens with its representation and how that representation is related to a representation of the Daha, but not the algebras themselves. So in some sense, they're cousins. Okay, so we have all these relations. As I told you, AQT contains 2 copies of this affine Hecke algebra. And what I'm going to tell you about now is, once you have all these 3 relations, how does it act on these vector spaces Vn? And essentially how we can draw pictures from them. Any questions up to now? Very technical, so I understand if it's a little bit dry. Or if I'm speaking too fast. That's also potentially true. Had a lot of coffee. All right, so moving on. So we have this polynomial representation. So as I mentioned at the beginning, we have these Vn's, right? They are basically just the ring of symmetric functions tensored with a polynomial ring n when the y's, y1 through yn, right? And again, to recap, we have V0 where we have no y's. That's just the ring of symmetric functions. And what we want to do is construct an action of AQT on this ring. Say that again? There's infinitely many xi's. Yes, yes, yes. Exactly.
Going on a very big picture is you take a group algebra of a symmetric group, and then you generalize in 3 different ways. First way, you make it a symmetric group on infinitely many variables. Second, you add t. Third, you add q. And so
So okay, yeah. Okay, so sorry. Let me back up a second. Okay. So for those of you who don't know what the Hecke algebra is, and you've just been staring at me wondering what on earth I'm going on about, you know the symmetric group, you know the group algebra of the symmetric group, right? And the Hecke algebra is essentially a quantum deformation of the group algebra of the symmetric group, right? So these relations here are analogous. These two are the same as you would get in the symmetric group for simple transpositions. And what you want to think about is you want to replace the simple transpositions with these TIs. But you also want to modify the relation that tells you that SI squares to 0. No, yeah, SI squares to 0? No, to itself, right? I don't even remember the symmetric group anymore. To the identity, thank you. SI squares to 1 for this relation, which is, this is where this quantum deformation is coming into play. If you've seen this, you might have seen this with Q's as opposed to TQ inverse. That's a normalization choice. You can essentially just treat this as its own parameter and just ignore it. Yeah. Okay. Is that helpful? Yeah. Literally speak up. So if you don't understand what I'm saying, just ask me. I'm happy to delve into that. Thank you for stopping me. Sometimes Q and T appear differently. we are pointedly in this normalization taking PQ inverse to kind of be the unit parameter that we're working with, but we will see P's and we will see Q's that appear separately as well. Yeah. This, just for those of you who might care or understand, there's the reason behind that choice just has to do with the fact that we wanted to categorify this from the very get-go, and that normalization works well with Zergel bimodules, whatever that means. Okay, so we're back to this presentation, and what we want to do is construct an action of this algebra on this vector space. Why do we want to do this? Well, again, if you are familiar with Daha, or the double affine Hecke algebra, there's a well-known, again, polynomial representation of the Daha on a polynomial ring. So this is in some sense the analog that the natural construction that you would want once you have this algebra. How do you do it? So first of all, we don't want to act just on each Vn. We want to act on the direct sum of these Vn's. Why? Because we want to think of these d pluses and these d minuses as raising and lowering operators on these Vn's. So we want d plus, whatever it is, whatever it does, we want it to go from Vn to Vn plus 1. We want d minus to go from Vn to Vn minus 1. We want the ti's to go from n to n, and the ph's and the y's again to go from n to n, right? So this is, when we define this algebra, right, I said there's these idempotents, and you want to think of the ti's as going from n to n. That's exactly what these Vn's are indexing. Yes? Yes, and that's, I will explain this. Yeah, so in addition, we want to think about each of these Vn's as being graded, right? We can grade these by homogeneous degree in the x's, right? Homogeneous degree of symmetric polynomials. That makes perfect sense. So we're going to think of each Vn independently as being some sort of graded vector space here, right? And so we, in particular, can also say, well, let's say let the m here go to m go to m plus 1, and essentially play this game. So the m's are less important. Really, it's about the n's, and the idea is basically just that these act like raising and lowering operators. So that's the main takeaway. Okay, what is the actual action? So the action is as follows. We want yi and ti, right? Remember that these two generate this affine Hecke algebra action. We want this to be actually just a very classical action. So the yi's are going to act by just multiplication by yi's. Right? F's are supposed to be something that lives in this polynomial ring that has y's and x's. Y's are a variable. You can multiply by y's. Totally fine. So that's just what this is. Ti's are a little bit of a more complicated formula. This del I is what's known as the divided difference operator, which if I had a blackboard, I would just write it for you. But essentially, right, this is just going to say you're going to take the original function, you're going to symmetrize it, so you're going to apply si to f, so you're going to take xi, or in this case it's yi and yi plus 1, and symmetrize them, or flip them, sorry. And then you're going to divide by yi minus yi plus 1. So it's just a very classical operator. And this operator as a whole is known as a de Moivre-Lustig operator. And it's these two together essentially give you a very classical polynomial action of the Hecke algebra. So this is very old. This goes back to Lustig. In addition, we have these much more interesting actions, right? So d minus is going to act, as you see, by this very complicated formula. What is it doing? You're taking your symmetric function, or your polynomial, that's part symmetric function, part y. You're going to modify it through a plethysm. So, right, we're just basically taking our alphabet of variables x and modifying it by this multiple of yn, which is essentially just saying, let's include yn into our alphabet by this plethystic substitution. Multiplied by ek, that's the kth elementary symmetric function, multiplied by yn minus k, take a big sum, take a residue, and then rescale. Easy, right? That's clearly a joke. That's, very complicated. It's a very complicated action. And you do the same thing. D plus is some sort of plethysm. D plus star is also some sort of plethysm. I'm not expecting you to memorize these actions. I'm just showing you so that you understand what follows a little bit better. The point here is they're complicated, and it's hard to work with this if you're just looking at it. They're very differently. Yeah. They're very different. They're very different. Yeah. Which makes sense because you don't want their commutator to be 0. Right? It's this other operator phi that is essentially, right, from phi you construct yi. So you want their commutator to be kind of like multiplication by yi in some sense. Yes. Oh, great question. Yes, absolutely. Yes. So if you, at this point, haven't forgotten what our original motivation for studying this algebra was, right, this shuffle conjecture, somehow this algebra is supposed to tell us something about applying this operator nabla. Yes? I don't know, actually. That's a great question. I don't know. I've never... I don't know. Sorry. Okay, so you have this, so you might ask, where is this operator nabla showing up? Since it was supposed to be a way of figuring out how it acts, right? And this is exactly where this involution comes into play. So it turns out that on this big vector space, you can actually construct an involution, we're going to call it n, that intertwines the actions of d plus, or basically of the start and the unstart operators, right? And essentially, you can go from if you conjugate the unstart operators by n, you get the start operators, and it squares to itself, or to the identity. Obviously, it's an involution. Why is this operator interesting? Because when you restrict it to symmetric functions, it essentially is almost nabla. It's nabla composed with the standard involution on symmetric functions, which is just changes e's and h's, right? It swaps elementary symmetric functions with homogeneous symmetric functions. So we can basically think of n as being like nabla, but nabla just acts on symmetric functions, and we wanted an operator that acts on symmetric functions and all these like vi's, you know, vn, vn plus 1, etc. So n is in some sense, the natural generalization of this. Cool. Yes, we're treating Ti inverse as Ti star. Exactly. Say that again. What's your question? Yes. So the problem here is that what are McDonald polynomials for Vn, like V1, V2? So step one, if we could define such things, potentially. I don't know of such a basis yet. The actual definition is this. It's the thing that's uniquely defined by sending 1 to 1 and acting a certain way on these D pluses. So there's a piece that I'm telling you that I'm skipping over, which makes this actually make sense, which is the fact that you can actually show that each of these VNs can be generated by the D pluses. So it's sufficient to define how n interacts with the D pluses to actually know how it acts on each of the vector spaces. So if you take AQT and you act on, I want to say E0 here, right? The projection onto the 0th space. This is isomorphic to, and I think you take En here. This is isomorphic to Vn. That's what I mean. Yeah. So if you know how it acts on the generators, you know how it acts on Vn. Yeah. Okay. So good. So now let's move on to the actual topological content, right? That's the classical story. We did all this algebra. And what I want to show you is that this algebra, complicated as it may look, when you just when you look at all these kind of horrifying expressions that are very scary, is very natural when you see it as pictures. And And so that's what I'm going to convince you of, hopefully, if we don't run out of time entirely. So to do this, I want to first start by telling you what a topological Hecke algebra is. How do we view this Hecke algebra that I kind of glazed over and I now will define properly? How do we see it as pictures? So first of all, we want to start with the symmetric group. Right? What is the symmetric group? Well, my favorite presentation is in terms of simple transpositions. Right? I can take, again, this is the relation we talked about. These are what I like to call the Braid relations, and then you have sigma I squares to 1. If we think about each sigma I as taking, let's say we have n strands, and I want to think of sigma I as taking the ith strand and the ith plus first strand and just crossing them, then sigma I squared is this relation, right? That if I cross them twice, meaning if I stack them vertically on top of each other, you get the identity. Here, this translates to this, right? Because we're doing sigma I plus 1, sigma I. So that's basically the interaction between strands I plus 1, and I plus 2. That this is supposed to equal this. And this relation is telling you that the crossings can vertically commute past each other if they're in strands that are non-interacting. So what this tells us is that for any permutation, you can actually draw a diagram corresponding to it, right? We can think of the symmetric group as just pictures. Totally, so far so good, hopefully. And of course, we can think about the group algebra of the symmetric group. Same idea, we just define formal sums of these diagrams, nothing changes. And in fact, we can do the same thing for elements that live in the group algebra of the symmetric group. For example, we have Young symmetrizers, right? Or Young anti-symmetrizers, or Young idempotents in general. We have corresponding diagrams that we can, special diagrams that we assign to the image of these Young symmetrizers. So for example, if we have E2, the Young symmetrizer for partition 2, right, a row of size 2, that's 1 over 2 factorial times the identity plus the 1-2 transposition, right? Diagrammatically, we could think of that as 1 over 2 factorial because we're allowing, to have coefficients. And then we're going to think of the identity as being 2 vertical strands. That is really tiny, but we just want to think about this as 2 vertical strands, and then a simple crossing. The 2 vertical strands are the identity. It's the identity on every element. The crossing is the transposition 1 and 2. And so on. And so we can generalize this for basically n strands. We're not going to necessarily draw the full thing. We're just going to shortcut that and draw a little box and label it Pn and say, that's the nth symmetrizer. We good up to here? Does that make sense, maybe? Okay. So this is, in some sense, what I said before, right? The Hecke algebra is just a quantum deformation of this, which is a fancy way of saying it's the group algebra of the symmetric group where we sprinkle some Q's in some appropriate places, and we change this relation to that relation we saw before. And we relabel the generators, instead of calling them sigma I, we call them TIs. And what we want to do is we want to basically redraw this, but for quantum deformation, whatever that may mean. And we want to lift all these structures, these Young symmetrizers, to analogous constructions for the Hecke algebra. So how do we do this? Okay, so we have this Hecke algebra, and it's, again, we're going to define it as an algebra over QQT, because we can, whatever. And it's going to be generated by TI and TI inverse with the following relations. We have this relation, which was the same as in the symmetric group, this relation, which is the same as in the symmetric group, and then this relation, which is this modification of SI squared equaling 1, which maybe you've seen like this before. These are the same relation, just if you expand this out, you get this. And what we want to do is assign pictures to this story. Oh, wait. Yes? Sorry.
Doesn't have tau I.
Yes, but it has a tau I squared.
Ah.
And so you can just multiply both sides, because one side is 0. You can multiply by tau I inverse. And you have a term that's identity, right? Like minus an identity here.
I see.
Yeah. Okay. So we're going to draw pictures for this. I'm going to say, let me draw TI, rather than just a crossing where I don't keep track of whether it was over or under. I want to keep track. I wanted to add an extra dimension and allow my crossings to have some depth to them. So here, the TI is going to go to this crossing, which I'm going to call a positive crossing, which just means the leftmost strand goes over. TI inverse is going to be, well, the inverse of this, which is you take your left strand and you go over, right? And the idea here is if you compose these two, i.e. if you stack these two pictures one on top of the other, you get two free strands, which is the identity, right? And the relations are the same thing as we saw before, but now we are keeping track of these over and under crossing informations, right? And then this relation, which is in some sense the defining relation of the Hecke algebra, is naturally translated to the following expression. And it turns out that if you study low-dimensional topology, you will recognize this relation immediately as the Skene relation. So then you're like, oh, wow, this is really great. Can we take this further? Like, can we draw pictures for everything else? Any questions? Oh, yes, absolutely. Thank you. I forget what has been asked already, but I will keep that in mind. Okay, so what this allows me to do is to take any element of the Hecke algebra and draw a braid. Just like for the symmetric group, any permutation I could draw a diagram. I can think of these as just braids, and for any element of the Hecke algebra, I get a braid. Right, so I can think of the Hecke algebra as just essentially being the span of these, braid diagrams, mod the Skene relation, right? Modding by this relation here, over QQT. So we're taking coefficients in that ring. And we can do the following. We can say, well, the Hecke algebra, certainly we can act on it on the left and on the right by itself, right? That's just you multiply on the left and on the right by an element in the same algebra. We want to think of this as taking W and acting on the left by A and on the right by B. And this can be translated to the land of pictures by saying, well, let's stack on the top and on the bottom. So the top and the bottom action are the left and the right action correspondingly for the algebra. And so one thing that you can do, which you can't see, unfortunately, is you can ask, what happens if I take Hn and I quotient by its commutator, right? What is quotienting by a commutator in this context do? It's identifying the left and the right action. It's saying, let me pretend that acting on the right and acting on the left are the same. So if we think about this as a picture, we're saying, well, I want the top and the bottom to be the same. I want an action on the right to be able to come around and act on the bottom. I want an action on the bottom to somehow be able to come around and act on the top, which is exactly telling us that this Hn mod its commutator is nothing more than taking these diagrams and closing them, right? By closing them, we are essentially identifying the right and the left action. And so this commutator is just the span of these diagrams closed up. We want to close them around an annulus, essentially, right? We want to pretend there's a puncture in the space that we're closing them in. And what that does is it prevents us from taking that innermost strand and wiggling it back and moving it, right? There's a little hole in the middle that gives you some structure to the manifold that you're working over. And again, we're taking braids up to the Skene relation, right? These Ds can be any picture like this. They're coming out of the D. So here we want to think about all the arrows going upward. Yeah, that's a very important point. Yeah, so they go up out of the D and they go down when they reach the other side of the puncture. So it's up and then down. Oh, there's not an arrow. In the puncture, there's just a hole. I just put a dot there to remind myself that there's a puncture. Yeah. But in some sense, you want to think about this as just living on the inside of a donut. Right? That's all. A thickened annulus, or the inside of a donut. Cool. Any other questions? All right. So why am I going off on this rant? Because there's a theorem due to Morton and Aston that tells us that if you take the direct sum of these consecutive quotients of the Hecke algebra, you actually recover the ring of symmetric functions, right? And so we were interested in saying, well, the ring of symmetric functions is cool, but what about these VNs? These VNs are in some sense, I don't know, a polynomial generalization of the ring of symmetric functions, right? They're symmetric functions with some extra coefficients in y's, some extra polynomial variables. And so we might ask, if I know what V0 is just the closure of these diagrams, how do I incorporate y's into into these pictures. I guess what I'm saying here is that the question. Oh, yeah. So your question was, is this theorem that I'm giving or claiming belongs to Morton and Naiston, does that belong to Turayev? Is that right? It was my impression that this isomorphism between this quotient and the closure of these skein theoretic construction was due to Morton and Naiston. I think it's in her thesis, but maybe I am mistaken. And yeah, I'd be happy if I'm wrong. I'm happy to correct it. Yeah, I'm gonna have to ask you for a reference after that because that's obviously an important point. Okay, so as I was saying, a natural question is, well, I want to incorporate the y's, right? Somehow I'm trying to take all this algebraic construction that I gave you and translate it to topology. So one thing I can do is, rather than quotient, right, here I had hn mod its full commutator, I can think of taking a partial commutator where I have hn plus m, and I'm only identifying hm with hn plus m. So I'm only taking a little sub-piece of it. And it turns out that this quotient, this kind of partial quotient, is the same as taking these braid diagrams and not identifying all the strands, but only the rightmost m, right? Where here m is this smaller piece that you're gluing together. Right, and here you would have n strands essentially just free, that you're not closing. And one of our results with Matt Hogenkamp is precisely this, that this vector space can just be realized as diagrams of this form, where, remember that Vn was graded, it was Vnm, where n was the degree of the y's, and n was the number of y's, and m was the homogeneous degree of the symmetric polynomial. So here, that's exactly what this is doing. This is basically saying we can take m strands, we can symmetrize those in some sense. We can treat them as symmetric functions, which topologically corresponds to closing them. And then we can take these n strands, which are just polynomials and are not symmetrized. And these are essentially corresponding to the y generators, right? Okay, so we can take the span of diagrams like that. And in addition, we want to add an extra condition. We want to claim that the action on the bottom here, on the ends, by the Hecke algebra is trivial. So we do this by saying we want to pretend that there's a little symmetrizer, a little young symmetrizer living on the bottom that absorbs any crossings. So if I were to act on the bottom by a crossing on these n strands, it would leave it invariant. Whereas if I act on the top by a crossing, it actually does something non-trivial. And this is a technical condition. For the isomorphism as a vector space, you don't need it. But because we are interested in constructing an action of this algebra on this space, we added this technical condition. Any questions? Okay. So once we have our vector space, the next question we might ask is, how do we construct an actual action of AQT on the vector space? How do we realize all these complicated plethistic operators as pictures? Can we recover this polynomial representation? And the answer is yes, you can. So I'm just going to give you what the operators are, essentially. So suppose here, right, this is an element of our vector space D. This is a generic element living in Vn. And I want to define how Ti is going to act on this diagram. And it's going to do it by taking the ith strand and the ith plus first strand and just crossing them. That matches with the action of the Hecke algebra and its description topologically. I want D minus, which was this lowering operator that was supposed to go from Vn to Vn minus 1, to be essentially the only thing it can be. It's going to take a strand, the nth strand here, it's going to wrap it around the puncture and close it, right? And this is why when I was defining this in previous slides, I was very careful about keeping track of the n's and the m's, because in some sense, this is telling me exactly what the picture has to be. Sorry, the buzzing is really annoying. Stop. So this is in some sense telling me exactly what the picture has to be, right? Because I want something that has n strands to land in something that has n minus 1 free strands. So I'm going to take that free strand and close it with itself somehow. And I also want the number of the homogeneous degree of symmetric polynomials to increase. And that's exactly what I achieved by closing it around the puncture. D plus is going to be, well, I wanted to go from Vn to Vn plus 1. So I need to increase the number of strands here. So I do precisely that. And since my pictures have to have a symmetrizer on the bottom, I basically glue a little symmetrizer on the bottom. I glue a multiple of it, but it's morally the same thing, right? Phi is going to take this n strand, wrap it around, and bring it back. Yi, which is this Hecke algebra or affine Hecke algebra operator, is going to take the ith strand, wrap it around, and bring it back to position I. And likewise, we can define operators for the starred, or we can define diagrams for the starred operators. Now, if you're not familiar with topology, this might look really, really weird. But if you remember what the definition of D minus was, which was you take a symmetric function, you take some plethysm, then you multiply it by EK, then you stick it in some weird long series, then you take its residue, then you do some other stuff. This isn't so bad, right? I think this is actually very nice. You take a picture, oh, you close it. I can do that, right? D plus and D plus star with these crazy residues as well. So part of the benefit of having a diagrammatic description, as we'll see, hopefully, is that we can compute things much more easily. And there's a lot more intuition. If you're interested in studying things about this algebra, things about this action, there's a lot more intuition when you draw these pictures than if you're looking at these complicated formulas. Unless you're great with plethysm, and maybe you get a lot of that. But certainly, I find it a little intimidating. Yes? Yes? My pictures don't involve TQ inverse. My pictures come from the Hecke algebra. Yes, but I'm expanding my polynomial or my base field so that I can multiply by T's and Q's. That's not a problem. Yeah. That's and if you remember, I defined my Hecke algebra to be over QTQ or QT, not over QTQ inverse, intentionally. Yeah. Okay. So, wrong direction. So then, theorem, these diagrams really do encode the topological action of AQT on this vector space and realize the polynomial representation. And actually proving that is very, very easy because you just draw pictures and you show that the pictures are the same, right? And I mean, and this is part of, in some sense, the justification behind the construction. You look at D minus phi. This, one of the relations, one of the many, tells us that D minus phi is supposed to be phi D minus Tn minus 1. If you draw the corresponding pictures, right, here phi, what is it doing? It takes this strand and it wraps it around. D minus takes the next strand and it closes it. This one here, first does a crossing, that's the Tn minus 1. Then you take the next strand and you close it, that's the D minus. Then you do phi, which takes the next strand and it wraps it around and brings it back. This picture is supposed to be the same as this picture. Proving this with the actual definitions in terms of these plethistic operators takes some effort. If you draw the pictures, you take this crossing, since these are supposed to be topological pictures, you can wiggle them. They're honest, just braid diagrams. So you can take this crossing and just move it around to this position, and you get that crossing. They're the same, right? Because we're allowed to manipulate the pictures like topological objects. And the proofs for basically every relation are like this, right? This picture is supposed to be the same as this one, and all you're doing is just wiggling the strands. So the relations become entirely trivial, right? And what's amazing about this is that the only relation realistically that we imposed in any of this is the skein relation. So it all follows naturally from the skein relation, from the topology knows exactly what this algebra has to be. And just as a comparison, let's look at the original definition, a little bit less friendly. Probably. I just have never thought of it. I've never asked myself that question. Yeah, whether the question was, can I use this to show whether my representation is faithful? Probably, but I don't know. I've never, again, not a question I've pondered. Okay, so the next thing you might ask is, what about nabla? How does nabla fit into this diagrammatic construction? Right, and the way it shows up is via essentially just composition with what's known as a full twist braid, which again, from a topological perspective, is an incredibly natural operator. So for those of you here, and I apologize if you're at home and you can't see this, but here in the audience, so the full twist braid, let's say full twist 2, is just, you take 2 strands and you cross them entirely past each other as many times as it takes for every strand to return to its original position. So this was strand 1, it returned to position 1. This was strand 2, it returned to position 2. Full twist 3. We start with 3 strands, we cross them. That's one crossing. Everything is not back yet. We do another crossing, and then finally we do one more crossing. All right, so here 1, return to position 1. 2, return to position 2. 3, return to position 3. Right, that's the full twist. So here we're just doing that for n plus m strands. The full twist commutes with with everything. It's a central operator. So there's a lot of reasons for why we like full twists. And in addition, we want to take our diagrams D, which are some sort of braid diagrams, right? And we want to replace essentially the TIs with TI inverses. That's this involution component that we saw previously. So it changes a crossing that where the left strand goes over to going under. And it changes QT to QT inverse. Okay. And then you can show, again, by just drawing the corresponding pictures, that it really is an involution, it squares to itself, and it conjugates the 2 actions, as we would expect. I have 2 minutes. Okay, I will hurry up. So I was going to give you an example of how it really does conjugate the unstarred to the starred operators, but this is really just an application of checking the diagrams and showing that up to wiggling, everything works. So maybe let me tell you how this relates to symmetric functions. The fundamental takeaway from this, or one of the most important consequences, is that a lot of the symmetric functions that appear in the proof of the shuffle conjecture can be realized using these diagrams, right? So for example, an elementary symmetric function viewed as an operator acting on Vn can be drawn. It's this picture where you take essentially, you add a strand, you wrap it around k plus 1 times, and that gives you the k plus first elementary symmetric function, right? In particular, if you set n equal to 0, you just take this strand, you cross it k plus 1 strands, and you close the diagram. That's ek plus 1. Hk plus 1, the homogeneous symmetric function, is the same thing with the crossings reversed, right? Nabla En then becomes, well, you take this, crossing where you take the first strand, you cross it over the other k, and you compose it with a full twist on n strands. So this gives you just a beautiful description of what this Frobenius character is supposed to be. Parking functions and a lot of the other symmetric functions can be interpreted as diagrams. All Littlewoods, all of this, they have analogs as pictures that are completely well defined. And so maybe let me end with the following computation. Suppose we wanted to compute nabla E2, and suppose that one of the things that you wanted to show was that nabla E2 really does decompose into the sum of combinatorial symmetric functions that the shuffle conjecture, or the shuffle theorem really, says it does. Well, you can just compute it very easily using the pictures, right? So here, nabla E2 is supposed to be this. If you rewrite the full twist on 2 generators, that's this little piece right here. There's a couple of recursion relations that you have to apply because you have little projectors or little symmetrizers that are running around, but this is not that mysterious. And you just apply it, and essentially you end up with a result where you can, as I told you, you can classify these symmetric functions once you have an appropriate dictionary. And by looking at this, you know that this is the symmetric function that corresponds to the dict path drawn below. you know that this corresponds to the second elementary symmetric function. And if you compare this with what the combinatorial formula, nabla E2, is predicting, you'll see that it agrees. So you can give me one more minute. Let me just end on some future directions. Why do you care about this, right? Can you draw some nice pictures? It makes the action a little bit nicer, maybe a little bit less scary if you're into topology. Well, one of the reasons that you might care is that it allows you to actually construct new operators on the ring of symmetric functions that are not obvious from the perspective of the algebra. Right? There's a lot of things that you can draw because they're just pictures. You can say, oh, what if I took this strand and I did this? What if I took this picture and I did that? Right? That are natural from a topological perspective, that if you were to rewrite them in terms of algebraic symbols, it'd be some awful plethystic craziness, something that you probably wouldn't just come up with. But topologically, they make a lot of sense, right? And so one question you can ask is, well, what are these very natural topological operators corresponding to in the land of symmetric functions? And can they help us solve other conjectures about symmetric functions that we wouldn't be able to address because somehow we wouldn't have this extra intuition, right? Certainly, a very important connection is the connection between the Qt combinatorics and not homology, right? So I alluded to this at the beginning. There's a lot of conjectures that tell you that a lot of the formulas that come out in Qt combinatorics should be predicted or should be able to be proved if you know how to compute these invariants, these homological invariants for knots and links. And lastly, and this is, again, I alluded to this, I didn't talk about it at all, a follow-up to this result is the fact that we can actually construct categorical analogs to everything here. And that gives us a categorical understanding of it. So if that means anything to you, well, I'm happy to talk about it. But if not, just ignore it. Thank you. That's all I want to say. Go.
Both from the audience and from the Zoom. So possible.
Yeah.
How long don't think they're having?
Yeah.
I have a question. I have one question.
Yeah.
Which is, do you get monomial symmetric functions as some nice pictures?
Do I get monomial symmetric functions as some nice pictures? No. We get power sums as some nice pictures. Sure functions can be understood. I've not managed to get monomials as anything particularly nice. No.
I have a question.
Can you maybe prove, maybe does your method give a new proof of the shuffle conjecture?
That I've thought about. Does this give us a new proof for the shuffle conjecture? Unfortunately, no. It gives us a different interpretation and a different way of understanding, but fundamentally it's the same proof that was given by Eric and Anton, so Carlsson and Mellit. Because we're basically, right, when we're saying that nabla E2 equals this, we're using their technology implicitly by using their operators. Yeah.